Hello everyone, I'm Yousef Nademi and I'm going to present the performance optimized hierarchical model predict neural response in higher visual cortex. And this paper has been published in the year of 2014. It's quite an interesting paper and pioneer in modeling the IT section of the brain. And another interesting thing is this paper has more than 1,000 citation, which is pretty high. And I'm gonna walk you through the paper. But before jumping into the paper, I'm gonna introduce give you some backgrounds on how to decoding part of the neural activity is happening. So let's jump on it. And so, if like to give you an introduction, when we see an object, like as a human, we immediately can identify what the object is, and no matter how distorted, no matter how like it's the position, lightening, or many other sorts of noise or variations, we are as human can effortlessly identify those objects. And the section that is kind of hypothetically is the part of the brain that do this object detection is IT, which is called inferior temporal. So you can consider this as a hierarchical sequence of a structure of neurons, and which start from V1 and vertical cortex. All of this is considered as a vertical cortex. Start from V1, which you can consider as a first layer of convolutional neural nets when we have like uh, where it can detect the edges, the lines, and those simple characteristics of an image. And then we have V2, which is the information passed on from V1 to V2, which can like identify the shapes. And then later on, we can objectify the objects. And then later it will go to IT, which is all the processing and all the object detection is happening. And we can identify that object is happening in the IT. So I'm going to give you an introduction of how this understanding neural algorithm is happening. So the informations that we our central or vision sensor is coming and we see those objects is encoded in patterns of neural activity. And these techniques like neural decoding will help us to understand how information is being transferred as it travels through the brain. So, as I said in the before, it's gonna start from V1 and go to V2, V4, and IT, which is like decide what the object is and detecting it. So imagine we wanna like measure a response from some sensors that we implanted in any of these regions. But for now, imagine as IT. And we have, in this case, is a simple case, we have 6 neuron sites that we implemented those sensors, and we're recording the activity of those neurons and how much they're firing by showing them some stimulus. In this case, the stimulus was a car, and we know that the neuron, like the site 1, has been fired at this level, neuron 2 has been fired at this level, and 3 like the highest, and later on goes on and on. And we can represent this as a color mapping in a way that the redder the color is, means that the neurons is more active, and the whiter and bluish the color is, the less active that neuron is. So when we encode this, and the purpose of this neural decoding algorithms or methods is to give it this neural activity, and it can predict us what the stimulus was. And let us walk us through how we can do such a framework. Imagine we have a monkey and we're showing them an object of a kiwi in this case, and we measure the neural activity in the IT sections or any other region that we're interested in. In this case, as I said, imagine this IT, and we measure the neural activity of all the sensors that we implemented in. And the neuron one, or site one, fire these kind of specific patterns, neuron two this way, three, and etc. And then we give this to a pattern classifiers, and the job of this pattern classifier is that needs to tell us what that object was, and we can decide is it true or false. Similarly, if the assumption is when we show a different category, in this case is a human face, to a monkey, the activity of neurons and the amount of that they're firing will be different. So the pattern of this, when we give it to again to the pattern classifiers, need to identify that object, and in this case, you need to tell us that was a human face. And if the prediction was make a predictions, it's gonna give us kiwi, and if it's correct, we say it's correct. If it's false, we need to improve the parameters of these pattern classifiers to predict for this this training data or training neural activity. And similarly, if the prediction was a human face, but the actual stimulus was on car, so we know that this classifier is not doing a good job, so it needs more training, or we need to adjust the weights in a better way. So how this neural decoding has been learning is that, imagine in this case we have a simple case of a face or a car, F abbreviated for face and car, and these are the neural response from the sites that we measured, and we show a bunch of face and bunch of car pictures, and we record those neural activity, and then we split this into this training data or training neural activity into a cross-validation split. And in each split, we training on two of this and tested on the remaining data. And we train this neural activity to correctly estimate, correctly predict what was the stimulus that has been shown to. So imagine we've done a bunch of trial, and for kiwi, and based on this 6 neuron activity, we have these level of algorithms, or this level of firing of neurons is happening. And as I said, we can do it like a linear classifier or a SVM or correlation, like the maximum correlation estimator to predict what's this cases. So imagine we do a simple case, or we're training based on this data, and the algorithms learn these prototypes, which says that these are the neural activity of the kiwi, and this for face this is the representative of the neural activity of the human face, and etc. Up to a category, in this case was a car, and we can say that these are the patterns. So, and we have some testing stimulus from the same objects that we show it to that human or monkey, and we want to know, and we recorded the neural activity is this way, and we want to predict is this neural activity is a kiwi or as a human face or something else. So we give it to this we can compare this with this learned prototypes, and we can say that it's it's pretty similar to like Kiwi in terms of response compared to the other one in terms of the similarity function. And then we can say it's a Kiwi. So and then we know what we showed to that object or human or monkey, what was the stimulus that gave us to this, and if it's predicted correct and it was a Kiwi, so we say that the algorithms or this neural decoder is working correct and perfectly. And how they applying it? So usually they have a fixation point, and they show you a black sign and some fixation point, and ask us to focus on those white spot. And they measure the response from like starting from 500 milliseconds, depending on the experiment setup, it will be different, and then testing it on the next 100, or depending on this sliding windows, up to us to decide. And we expect that from minus 500 uh, milliseconds to the zero, because we haven't shown any stimulus, so the predictor needs to predict some random based on the classes. So imagine if we have 7 class, so the neural response need to be 1/7, the performance around that, unless this monkey or human is very like good, can predict above the chance, and which is highly unlikely. And then from 0 to 500, so we give it to the show the stimulus at this time frame, and we expect that the neural decoder start to give us some accuracy, and it's able to predict the class that this car is from. And this is representative of it. So from minus 500 to zero, you'll see like the neural response is kind of above the chance, around the chance of what's that prediction is. Depending on the category, this will be different. And then when we show the stimulus at this time frame, we see that the neural activity and the classification accuracy will increase significantly. So this is a very, very basic neural decoding algorithms that I like was interesting, and I thought that was interesting to present how this will be calculated. So another kind of example to make it more concrete. So imagine we showing the objects or human or monkey some different distortion or angle of, in this case, of human face was Joe, and this hyperparameter space, this high dimensional, in this case 5-dimensional neural space, it shows different response at the different locations in this region, and decoder as well give us a different neural activity, but we're not talking about model for now. And then we show a different image, in this case was Sam, and it's going to show a bunch of different surface, and we expect that the IT section of the algorithms or the brain sensors can have a different kind of space, that when we apply a linear classifier, in this case a support vector machines can correctly separate these two spaces, and then we can say that this is like Joe, this is not Joe, something like that. So that's the purpose of neural decoding as well. Hopefully that this is more concrete in terms of what I said. And then another things that I want to emphasize, and that is another class of metrics for presenting the data of neural activity or the model prediction accuracy. And the way that they calculate this representational dissimilarity matrices they calculate the covariance between two different stimulus. So imagine we have a car and a face, and we measure the covariance between those two, and we reduce 1 minus 1 to make it dissimilarity. And if we wanted the similarity one, we didn't need the 1 minus 1, so it's going to be the similarity of it. And to make this more concrete, so this part of the image that I have is what's in the paper, and this was just I grabbed it from a different paper. So what it represents is kind of creating this confusion matrix, in which we see the training are in the left side, and the testing of those images on the top. And we expect that based on this, when we have 0, means that there is perfect correlations. When we have 1, because the correlation means 0, so there's no correlation. And we have perfect anti-correlation, which is 2, we can have these numbers and a range of between these. And then we can say we expect that when we show you a human face and the response is the same face and the space are these activity patterns, and then if we look at the correlations using the formula that I show you, they need to be very similar and the correlations to be perfectly correlated. That's in the perfect scenario. So it's symmetric in the diagonal, and we see that if we show this face of maybe Tom, and we have a face of maybe Ashley, and you see that there is this kind of similarity because the human face are objectively similar, so we might miss it, the correct correlations, and we see these things. But when we see the maybe a house and a face, which is completely two different objects, so we expect that those neuron activity will be different. And these pictures can also, like, you'll see it a lot of these imaging paper, but I'm going to discuss it more on the right spot. But that's give you an idea how these things. This is literally a confusion matrix based on the dissimilarity representative, and we have these objects in the x-axis and y-axis, and these show the correlations and the similarity between these two different objects. So going back to the claims of the paper, so the paper is claiming that there is a strong correlations between a model categorization performance and its ability to predict individual IT neural unit response data. By models categorization performance, I mean the models that they proposed, which I'm going to discuss in the detail, but this is just give you a broader picture. And we have a modeling approach. They have a modeling approach that can do a good prediction is in modeling inferior temporal cortex, which is the highest ventral cortical area. And their model is highly predictive IT spiking responses. And the modeled intermediate layers are highly predictive neural response in the V4 vortex or mid-level visual area that send this information from V4 to IT. Another things that the papers talked about was a lot about the explained and unexplained variations. So I want to give you a definition so we are on the same page. So explained, we have a total variation. These are statistical terms. So imagine we have a prediction of we want to predict y, and y is actual value of the prediction. I mean the actual value of the thing that we want to predict, and y star is y bar is the average of those predictions, and the difference between the average value and the actual value, summing them up, is going to give us the total variance that we have. So in this total variance, some portion of it is explained variation, and some percents are unexplained variation. So the explained variation is Y hat means like what the models predict, and Y bar is what's the averages. So difference of those two, summing them up for all the data points, is going to give us the explained variation. And an unexplained variation is when we have the actual value and we have the predicted one. The difference between these two means that how much the model missed the predictions, and we want this to be like as lowest as possible. It's going to give us unexplained variations, and we have the coefficients of determination, which can uh, be calculated in statistics by dividing these two explained variations divided by total variation, which means that how good are our predictions or how good our modeling is. So in this study, they use this, I don't know how to pronounce this, a type of monkey, which is very strange look in your face. And they put 296 neural sites, I mean sensors, and they place 168 of those neural sites are in IT, and 128 of them are in V4 part of the brain, which are they assume that they are the visually driven part of the brain. And they testing the images for the testing images. They show 100 millisecond, and they measure this firing spikes from 70 to 170 milliseconds after this firing has been removed, and they measure the stimulus presentation, which is it's been saying that these are the main regions that gonna give us the good representation of the stimulus response. And they try a bunch of different categories, and they tried in 8 categories and 8 objects per categories. They have animals, boats, cars, chairs, faces, fruit, plants, tables, and they impose a different kind of variation. Excuse me. They impose different kind of variation, including the pose, position, scale, and background variations. So the reason of background is they don't want their models or the brain's activity learn something about the background. So that's why they keep changing these backgrounds as well to like you focusing on the objects or the models learning the object as well. They have a screening image set that they also test on the response of the both neural activity and the model's activity in that sense. So they, for their modeling part, in addition of their own model, which I'm going to introduce next, they try it on a different set of models. They tried on pixel models. So literally in the pixel models, you have an image of 256 by 256, which is the actual size of the image. You flatten it out, and it's going to give us the 65,536 dimensional feature representation, in which we do the classification, which leads to a low accuracy. And that's our kind of baseline. You can compare this to that. And they have another algorithm, which is a scale invariant feature transform, or SIFT, which is a computer vision algorithms. I have a video, but I'm not going to show it. But if you're interested, you can go and watch it. It's talking about how this SIFT is working. Literally, what it does is so what it does. They have a SIFT object detector in which they apply the SIFT detector, and that does it based on some mathematical algorithms. It's gonna detect those relevance objects and create a histogram. And from those detected objects, you measure the orientation of each pixel, the magnitude of each pixel, and their orientations. And then we create histograms of those gradient direction based on the SIFT area of interest, and which they can compare it with the same image, and they can capture those objects, which is invariance of the transform that we might have in large or small or something like that. And they have a V1 model, which is based on the Gabor filter, which the person who proposed this idea was it's a linear filter used for texture analysis, which essentially means that it analyzes whether there is any specific frequency content in the image in a specific direction in the localized region. And conceptually is similar to the first layer of CNN, which we see the edges and lines, those kind of detections is happening. It's not doing a high-end kind of object detections. And we have a V2 like models, which is composed of conjunction of Gabors, similar to that, but it's not high level as well. And they have HMAX, which is a multi-layer convolutional neural nets targeting to modeling higher ventral cortex. And we have also applied on plus 09, which is they said recent, but like back then it's not recent anymore. It's a 3-layer convolutional neural net and a category ideal observer. So this categorical ideal observer, this model has 8 features, one for each of the 8 categories present in the test image set. For each image, the highest feature is the first is 1 if the image contains the object of I. Otherwise, it's 0. So for each IT unit, the 8 linear regression weights for these feature sets effectively describe how much each category contributes to that unit's response. So now going back to what their model is and what their proposal model is. So they have a proposed model based on the CNN model class, which I'm going to go through in details. And literally, you can consider it, this is the image. They have 1, 2, 3, and 4 layer, and representative of kind of V1, V2, V4, and IT. And for L1, each one of these boxes represents a set of convolutional neural net, could be and has a multiple operations like the number of filters, the threshold, saturations, pooling, and normalizations. So each filter, you can assume it as a convolutional neural net filter, which each filters do some part of object detections. It do like maybe edges, something like maybe it's some part of the face, and other filters do something else. And they have, I think, up to 21 filters, which can be have it in different setting. And they have threshold and saturations, which they apply a different threshold, means like when this unit is going to be activated, we can set up the numbers that when this number is above this threshold, this neural will be activated or deactivated. And they have a max pooling or average pooling layer, and this one is also can have a different size, different shape in terms of when they're applying it. And they have a normalization as well, which is a typical approach they do in the CNN. And they have a hierarchical stacking of these layers up together. And it's what I mean is that this is one separate network. This is one separate. This is one separate. This is one separate. And these combination, like attaching or stacking 3 of these layers together, is a different networks. And I'm gonna go back again to this, but consider these each points in here represents one of those configuration of these images in that space. So it means like this one might be like a 3-layer stacking, might have maybe 21 filters, like max pooling or average pooling or different parameters, and they have this one performance in terms of ITX invariance and the categorical performance, something like that. I'm going to go back to that. I'm just going to introduce it. So they have this L1, which is gonna say, as I said, it's gonna like detect those low level features, and then they have other, networks as well, which when they stacking them together is gonna do more complicated stuff, and they're gonna do a better performance. And going back and forth between these two, all these points in this A plot is based on these three layers. There's nothing based on the layers that I'm going to talk about. And actually, no, they have this as well. Like some of them have it, which is what this L4S does is gonna linear combination of all these other models that we have, which is gonna bring us the networks into 1250 feature vector, and this X is the image is a 2D input image, and what this stacking operator means, like how many of them are stacked together, and they have another operator of like a plus sign, which means that which one of these are combination or arrangements would be giving weight to add up and to predict the models. So what they did is they see that they tried on a random kind of configuration, which are the green color means that they see that the performance is not good in either in IT or not in categories of performance, and they did some categorization performance optimizations. They see the optimization goes up, the categorical performance, but IT explained variance is not that great. But when they parameterize the parameter of the algorithms to do good prediction, i.e. the IT fittings, they see that usually the one who is good at giving the IT predictions are also good at increase the categories of performance. So the idea is if they're able to train the model in a way that this can do a better job at categorizations, can also do a better job of explaining the explained variance of IT sections. So based on that, they have a optimization algorithms like Adabus. So in which what I mean, they explore a bunch of different space of the parameters. So to give it in a simple context, it means that imagine these three-layer networks. Of the first layer network structures is good at detecting some parts of, or some image classes. So do a very good job on those things, but it's do a poor job on other category or different one. But the second one, what we do is going to give more weights to the one that the first models weren't able to do a good job. And with this way, we optimize the second two. And then the third one, we give more weight to the classes or to the images that the algorithms weren't good in the two previous networks. In a way, in a sequence kind of parallel training or parallel optimizations, they can do a good jobs in doing, and also they updated these weights as well in this area. These images kind of fancy way of showing those spaces, and it's going to lead to the performance and like giving you the high performance in predictions and high performance in the IT explain. And you see after a bunch of optimization, it will give you these are the hierarchical model that they propose, and it do good jobs in both IT explain variants and also the category of observations, and it's kind of killing it in terms of compared to what was the state of the art at that time, like the CF Pixel V1, HMax, and Plus. All of them are lower in terms of both categorical performance and IT explain variance. So Going back again to what was the result, and these are the performance of their algorithms against other methods in this case. And you see, they, as I mentioned, they applied three type of variance. They have low variation, so image was close to the center, and the medium variation is kind of like shifted a little bit on the other sides, and but up to 45 degrees. While for the high variations, they can like rotate it up to 90, and like the level of shifting is a lot higher than the other two. And they see that the performance is this, their models, the red one is very good, close to the human as well. And as I mentioned, the human as well, what they did, they show this to the Amazon workers, and they do a bunch of categorizations and showing those, and they measure the performance, and they averaging those, and those error bars showing those averages as well. And then they see the IT performance, and V4 is like the model is very good in predicting IT performance up to all three levels. But in the high variation, medium variations, those other algorithms, state of the art, cannot catch it, and they're doing a poor job on it. Later on, they measure, these are the representative of like few sites that they show. Like they have the site 150, site 56, and site 42, in which they have black lines are the neural activity for 1,600 images for that specific. Each data points is going to show you the average neural activity of those images for that image. And it's going to start from like sorted by category identity and the variation amount. And the y-axis in each one is show the prediction response, the magnitude of neural site for each test images. So none of this has been used for the training both the neural activity classifier or their model. And they see that one interesting point is if you see that neuron firing is obvious. So you see that these sites as picking up like the usually chairs. The middle one is good at detecting faces, but the maybe right one, this site 42, is not that picky in terms of it's gonna show a bunch of different variations in terms of the object that it's showing. But the performance of the models, depending on if they look at the top layers, it do a very good jobs in 48% of the IT explained variants, which are the beans for all of these variation. On this yellow one is show the median performance, and the top one is showing the overall performance. As you see, the top one HMO is doing a very good job in predicting the IT explained variance, which is up to 50%. And it goes down the lower levels, is usually not very good in predicting all the variances existing in the image. And it's way better than state of the art algorithm in terms of IT explained variance. Like going back to the image that I show you, these are kind of average representative of the similarity or dissimilarity of this matrix. And what it shows is in here we have 64 different image type or image organizations, in which we have 8 animals here, 8 boats here, 8 cars here, etc., etc. The same arrangement, 8 animals here, 8 boats here, and we can compare them one by one. So the diagonals shows that should be symmetric, and also shows that it should be the lowest dissimilarity, as shown is the blue one. And these are the IT neural one. These are the prediction of the HMO model. As you see, the model is pretty doing good jobs in predicting this neural response in terms of image classifications, but the other low-level models are not doing a good job. But it's kind of showing it's completely matching. But they do also the object generalization, so it means like we have four animal objects or four boats, cars, in terms of objects, and they see the performance is also still good, and their models compared to the IT. So this is IT, this is HMO. And in terms of category, is a little bit not that great in terms of the models, but means that we need to consider still caching it in a good extent, but this lower performances comes from this neural identifications, means that the section of my image or my neurons activity, if we're showing a same stimulus, might be different from what your brain is showing, and etc. stuff. But if you compare it in this, like overall performance, HMO and IT is pretty good jobs, are very close, but the other algorithms is very low, and they're not doing a good jobs in explaining those variations or similarity or dissimilarity in this case. They also measure the neural activity of V4 site. They have 128 sites. And again, the black one shows the actual neural activity, and the red one is what the models predict. And the obvious thing that you can observe from this, there's no image preference as against to the IT one. And you see that there's no higher peak in terms of this thing, which in the previous case, if you remember, it was like kind of obvious that these regions have shows the higher kind of response firing. But in here, it's kind of not that the same level, and doesn't have that much of a categorical performance. It's doing so you can assuming it's gonna do it a high level objection. I mean, high level representations that IT can translate into those object classification. And again, like the HMO is doing a pretty good jobs to the top layers, means like the one that is have a linear summation of those, and like the up goes down again for like the parenthesis shows the level of the explanations and an average for all of them. And in here you can see that HMO is doing a pretty good jobs in the terms of top. In the IT one, it's like in terms of the explain one, explain variations, and beating all other state of the algorithms at that time. They do some other tests, but the idea is that they were able to perform a good model, and they did it in basic categorizations, and they tested on these kind of algorithm as well. They see that the performance is good, and then they did it on cars as well. You see that the performance is going lower, and when we have it's not basic one, I have a car itself. HMO is still doing a pretty good jobs, and also the IT one. But the face identification is the harder task. Still, with low variations, the performance is lower than the for basic categorizations, and it's gonna get very worse as we increase going to that side. This is also for testing for the variation performance, so meaning that the top one is saying how many training examples used for the training the HMO and VT and IT, and they see that's gonna be some variation between them, but the overall relative performance are quite the same. HMO and then IT and V4 are better object classification. It means that they're doing a good jobs in terms of number of neuron sites. They're saying that still with some we have a higher kind of variations. We need more neuron activity of IT side to do a good job. It's not as clear as the previous one, but still is distinctive between IT and V4 in terms of their performances. So overall, to summarize, so what I can say is, to me, it seems that they keep trying to maybe mimic the IT RDM by optimizing their models. They keep doing a bunch of linear, summations to see when they get the actual model performance. And they also measured only by two monkeys. The two monkeys might not be a concrete picture of IT neural response. What I'm as I said, like my neuron response activity might be different and will be different between your neuron activity and it be different by Dr. Fish activity, and all of us has a different neuron activity which we need to align. There are some neuron identifications with which we usually go through to aligning those neuron activity and do a better picture of those things as well. I can discuss it if you have or if you're interested. And also, they're saying that there's a proposed that 3 4 layer algorithms, but it's kind of hard to say it's actually three because they have lots of layer and lots of stacking, lots of filters, making a pretty complicated algorithms, and they are able to cache for these 8 categories. So if they increase the categories, the performance might go lower. Something to consider. And but the interesting part is this is kind of first study that they were able to kind of cache the IT. Before that, they weren't able to cache the IT good. They're usually good at predicting the lower level regions. And also another interesting is a quite extensive study, and the results are quite robust. And it's a very interesting. And thanks for this class to let me read such a good paper. And that's it. Because we're recording it, there's no question online, but we can and I can answer any question you might have during the in class. And thank you for your attention. And hopefully we'll see you and meet you on